Okay, here are your notes on 6.3 mechanical energy and isolated and non-isolated systems. Okay, so in an isolated system, that's where it's kind of a closed system. No energy can leave through any method. So that's like section 6.2. We were really focusing on isolated systems where potential energy would always equal our maximum kinetic energy. Okay, non-isolated systems, okay, there you can get some energy in or you can get some energy out depending on what it looks like. Okay, so isolated system, a group of objects assumed to be isolated from all other objects in the universe. An isolated system is frictionless, so the mechanical energy remains constant. So the conservation of mechanical energy, within an isolated system, energy may be transformed from one object to another or transformed from one form to another. Okay, so changing from kinetic energy to potential or the other way around. But it cannot be increased or decreased. Okay, so this is the law of conservation of mechanical energy. And so that's where, we really focused on this in our last section. But basically, in an isolated system, okay, your mechanical energy would remain the same, but then as your potential goes down, your kinetic goes up, and so on. Okay, the loss of gravitational potential energy is equal to the gain in kinetic energy. Okay, so the pendulum examples, okay, which we had one on our last section. As the pendulum goes down, as it comes up, it has potential energy. As it goes down, your potentials change into your kinetic. At the bottom of the pendulum, you have your max kinetic energy, your minimum potential, and then as it goes back up, your kinetic changes back into potential. So conservative and non-conservative forces. When a conservative force acts on a system, energy is conserved, mechanical energy is not affected. So because of your potential energy at point P equals the EK at point Q, okay, the speed of the car at Q is the same no matter which ramp it goes down, whether it goes on ramp B or ramp A. It doesn't matter that this one has more bumps in it. All that matters is your change in potential energy would be the same. It's all going to go to the kinetic energy at point Q. Okay, when a non-conservative force acts on a system, energy is not conserved. So mechanical energy is lost, and this usually happens due to friction. Okay, friction is a non-conservative force. Work done by friction is lost to its surroundings as heat. Okay, and again, work done by friction is equal to force of friction times the distance that friction happens. Okay, so for this example here with the non-conservative forces, the car travels a longer distance down ramp B, so more mechanical energy would be lost down ramp B than ramp A because of, again, force of friction has to do with distance. Okay, for the conservative one, we only have to look at this height. That's the only thing that changes. Okay, but now because we have friction, the longer the car tires are touching the road, the more distance we have, the more work done by the friction. Okay, and so our energy, some of it is lost due to the force of friction. Okay, and so again, we don't have to worry about these. Okay, these are the pages and the examples in your textbook. Okay, 311 to 322. Okay, again, I'll do a couple example type questions and then I'll send out the assignment for you to do.